So our next speaker is Blakesley Burkhart. He's going to be talking about dreaming of direct observations of H2.
Yep. Hi, everybody. All right, welcome back from coffee. I know we all love to get together and talk, and like lots of us haven't seen each other in a long time. I'm hoping my talk won't go the whole time. We'll see how that goes, so that we can continue to chat over dinner later on schedule. I'm going to talk about kind of something that's been a little bit blue sky for me for like the last couple of years. Thinking about star formation in the Milky Way and where that field is going. There's been probably, unless you've been under a rock or in like deep cosmology land, you've probably heard about Gaia and all the advances that Gaia has done for the ISM in terms of 3D dust mapping. I would say that's been like a revolution for the interstellar medium, and especially for the star-forming dense interstellar medium. And a lot of that great work has been done here at Harvard. And I've been thinking a little bit in tangent with that, like what are some additional observational probes that we can build up for the next generation of star formation studies? And one of those is to directly observe the molecular hydrogen in H2. So that's what I want to talk about today. And I've highlighted here my collaborators here, and I want to point out Shmuel Bialy, who of course is also a former ITC member who couldn't be here today, and I'm going to also highlight some of his work just to show him as well. And before I want to start talking about the science, I really just want to highlight and mention just how grateful I am that the ITC exists, that all of you are part of it, that Avi and all the permanent ITC members built it up over the years, that we could come together like this. I just had the most fantastic time as a scientist. I grew so much here as a researcher. And I was going last night through like the Facebook page, which I guess Mark Palmer probably manages. And he's done such a great job over the years of putting all these pictures up on the Facebook page. So I really encourage you to go to the Facebook page and just peruse. It's been 10 years since I arrived at the ITC, and there's definitely pictures from way before a decade ago. And there's so many goodbye cakes. You can see everyone's goodbye cake. And like the time that Avi had Stephen Hawking wish me a happy birthday. It was my 30th birthday, and I got Stephen Hawking to wish me a happy birthday. That was because of Avi. Thank you, Avi. That was amazing. And just all the great like group pictures. It was just such a great place. I'm so grateful. And Avi, like you definitely collected a lot of matches that, good matches that really caught fire. So thank you so much for everything. Okay, science, yes. So I've been thinking in my group, in my research program in particular, really about cosmic ecosystems and this gas star life cycle. And I've always approached this from kind of a holistic view, where, thinking about how gas goes from the very ionized, diffuse intergalactic medium into halos, and then from that, the whole baryon cycle of converting gas into stars, right? And how then ultimately feedback processes, both immediate feedback processes like stellar winds, jets, outflows, radiation, photoionization, back react on the gas. Of course, supernova being an important feedback process that then can drive galactic outflows. And of course, black holes also being very important for the intergalactic and ISM gas in terms of feedback. So this is quite a complicated picture. And one of the bottlenecks I would say that exists with this picture of gas cycling within galaxies is this atomic to molecular conversion and vice versa. This is a very sensitive probe also of the feedback from stars, in particular the photoionization feedback, which I think we have a lot of information from simulations, right? Hydrodynamic simulations can include non-equilibrium chemistry, radiation, et cetera. But the observations of these photodissociation regions are still kind of only piecemeal, right? And so what I'm talking about here is this interface between the fully atomic boundary and the H2 boundary. And as, of course, you go deeper and deeper away from the photodissociation region, you get into where most star formation gas is tracing with carbon monoxide and dense gas tracers here, where you're tracing the bulk of the molecular gas for star formation, which is also very cold, around 10 Kelvin or so. But we're really kind of lacking a lot of the diagnostics in this boundary region, right? Which is where gas is moving into the molecular cloud and also out of the molecular cloud, right? So the cloud is either maybe growing or dissociating depending on what the environment is doing. So there's, I think, a lot of open questions here which are really interesting, like the chemical lifetime of molecular hydrogen. How does that relate to the lifetime of this dense gas in the molecular cloud? The relationship between the molecular cloud, both the dense gas and the diffuse gas, and the star formation rate. What does that look like? How does the environment affect the PDR and also the dense molecular gas that's cold? Can we measure the formation and destruction of the molecular gas? And then, of course, the role of stellar feedback in star formation, which ultimately is dissociating the cloud. What really, is it mechanical? Is it photoionization? How does that regulate star formation? And we actually can answer all of those questions with simulations very easily, right? Because we can run a hydro simulation with star formation, we can put in all the chemistry, et cetera. But I really think we're not going to be able to really nail these questions down with simulations alone, right? We need observations, and we need observations particularly of the H2. So probably you guys remember from your ISM class, well, H2, okay, molecular hydrogen. Well, it doesn't have, it's a symmetric molecule. There's no dipole, so there's quadrupole, very weak quadrupole rotational vibration lines, which can only really be excited in warm gas. So long story short, everyone uses CO, right, to observe molecular gas. And you'll even see, this drives me nuts, observers. People put, the Kennekic-Schmidt relation, right, the x-axis is sigma gas, and they'll usually put big sigma H2, right, for the gas surface density. It's not H2, it's CO, right? It's CO that has been applied a conversion factor to convert into a total molecular mass. But it's not, in fact, the CO, or it's not, in fact, the H2. It's missing this, what we call dark molecular gas, which is basically everything that's not traced in the CO, not CO bright. So H2, right, so we can do H2 science with these weak quadrupolar lines in the infrared, and this is something James Webb is doing now. This is great. It provides temperature and density diagnostics in this warm phase of the H2. It's not a good tracer really of the diffuse gas around that PDR region though. It's collisionally excited primarily, not radiatively excited. So it's good for tracing dense regions, shocks, areas where the gas is warm. But really, if we wanted to trace that PDR region that I was just mentioning, we need to go to the FUV, right? So H2 also has many thousands of lines that can be radiatively pumped by Lyman-Warner photons, and those can actually be quite bright. And those can also trace this dissociation region at the boundary layer of the PDR. And the nice thing about those lines is the dissociation rate of hydrogen is directly proportional to the total intensity of those lines. So if you have a FUV telescope and you go out and you measure those lines, those particular lines, and you add up the total intensity of those lines, then you'll be able to predict the dissociation rate of hydrogen. You can also get a handle on the formation rate through measuring the lines and looking at the orthopara ratio, so the total nuclear spin of the H2. Can tell you something about the formation rate because from quantum mechanics, it forms at a ratio of 3:1 for orthopara. So anything that decays from that value of 3 is older H2. Okay, so you can do a lot with this. Why don't we have these diagnostics? Well, for the FUV, you have to go to space. Okay, so that's one challenge. Of course, there have been space-based FUV missions, so FUSE. I'm going to talk about a telescope called FEM-SPHERES a little later in my talk. But those have all been at very low spectral resolution. H2 has a beautiful spectra, a very dense spectra of thousands of lines. And so in order to resolve that spectra, you need much higher spectral resolution. So to get that, my colleagues and I proposed in 2021, 2022, a MIDEX mission to NASA, so Medium Class Explorer, which is a cost cap of $300 million. to do this kind of science, to map the PDR boundary regions. It was called Hyperion. We have a new version called EOS for the upcoming SMEX call, so the Small Class Explorer mission, which hopefully I think the AO will come out soon, so it'll be proposals for 2025. So the mission is very similar for the PDR boundary layer science. So the idea here is we have a very long slit that we will be able to place along local molecular clouds and map the PDR boundary layer in FUV, looking at these H2 fluorescent emission lines, and look at the formation and dissociation of molecular hydrogen. And the idea here is that we'll be able to get the dissociation rate directly from the total intensity of the lines. And here's kind of a theoretical mock spectrum of these lines. So you really need the 10 brightest lines resolved in order to do that. And then the formation rate of molecular hydrogen comes from modeling this orthopara line ratio, which gives you a chemical age. And so based on that, we can then compare that to other cloud properties like the cloud masses, the star formation rates, the star formation efficiencies locally within the molecular cloud, the particular stellar populations that are in regions of the molecular cloud, so higher mass stars, lower mass stars, et cetera. And I think it will really help us get at answering questions around this gas star life cycle. So I've been doing some modeling to kind of push along the science case for this mission. What might we see observationally? What kind of error bars would we expect on some of the observations? And to what fidelity do we need to make these measurements? Those kinds of questions I've been trying to help address with numerical simulations. And so for this, we wanted to look at simulations that had both good resolution in terms of resolving molecular clouds, but not being totally divorced from the environment of the interstellar medium on the large scales, and also having non-equilibrium chemistry to follow the formation and dissociation of H2 and the full chemical network. So we decided to use these Silk Zoom simulations. So the Silk collaboration, just play the fun movie again. There we go. Yeah, so there are zoom-in simulations that are taken from these tall kiloparsec slices of a Milky Way-like galaxy. And so individual molecular clouds are identified, and then the simulations then zoom in on them to achieve a 0.06 parsec resolution adaptively with the flash hydrodynamic code. And so you can see here some of the molecular clouds. This is the total gas surface density for the zoom-ins. And so what we've done here is just to take the Silk simulations and to look at the H2 formation and dissociation rates. So we have, the true formation and dissociation rates that are directly in the numerical simulations. So the formation rate depends on the total density of hydrogen, atomic hydrogen, and then the formation rate coefficient, which is taken to be a value close to kind of the Milky Way values for the H2 formation rate coefficient. And then the destruction rate is the number density of H2 times the the dissociation rate. And the dissociation rate basically just depends on the UV intensity. We're not considering other dissociation mechanisms like cosmic rays or X-rays. Those could potentially be very important in the ISM, but we're not considering them here. It's just the UV flux. And then, of course, H2 can shield itself, and there's also a shielding contribution from dust. Okay, so that's just the ground truth. And then synthetic observations, we measure destruction and formation from the total intensity of the lines for the destruction rate. And then the formation rate, we haven't done the full orthopara modeling here, but we're estimating the formation rate per area with an estimation of the atomic hydrogen column density times an effective N times the formation rate coefficient here. So this is how we're doing the synthetic observations. And this is work that Shmuel Bialy is leading. So here's Shmuel. Many of you know him. I wanted his face to appear at the meeting. So he has the true maps from silk and then the observed maps, and then we're looking at the observed over true. So this is basically what we're finding here is that regions of high shocks, high density, are very out of equilibrium. And so they also show high changes between the observed and the true dissociation rate. Similarly for the formation rate, the true value from the simulation, the observed. I mean, the good news here is that you can get the overall structure, right? If you were to imagine like mapping this cloud, the structure is preserved. It's very filamentary, these formation and dissociation rates. And then we can also potentially predict kind of what regions might we have problems in terms of our mapping. And then we find that these clouds are actually quite out of equilibrium, right? So a lot of times in the ISM, people assume chemical equilibrium, or even in simulations, they'll have a model of chemical equilibrium in their simulation. And we find in these out of equilibrium simulations, that's very much not a good assumption. You can have orders of magnitude of out of equilibrium regions in a single molecular cloud where either formation or dissociation can dominate. And this is oftentimes driven by inflows from the large scales or star formation that's proceeding locally. So it is really a dynamic process where you have this out of equilibrium chemistry happening. Okay. Right. So also we've been taking a look at just the general like rates and how they correlate with star formation. So this is not an observable, right? This is just purely from the simulations, how these things look, because ultimately we want to see if there's a connection between the star formation rate, star formation efficiency, and the growth or the dissolving of these molecular clouds, right? And so for the star formation, right, so the green line here is H2 formation, black line is H2 destruction, and the red line, or the blue line here is the star formation rate. And so the H2 formation rate, basically what we can find in one of these silk zooms is that there's a steady feeding of the envelope by cold atomic gas that's kind of outside the PDR boundary layer, and that can continuously feed the cloud. There's early times you can have predominantly H2 destruction that grows because stars are forming. So that's why it's lower at early times, and late times it kind of bounces around due to star formation. And then the star formation rate is very bursty in nature. And it can also at times outpace the dissociation. How am I doing on time? I'm going to move past this to show some of our summary plots. So here's an example of kind of a keystone plot that we'd like to make with this EOS telescope. We'd like to make a plot of the H2 formation rate divided by the star formation rate, and then the H2 dissociation rate divided by the star formation rate. So basically looking at sources and sinks of star formation and the molecular gas. And so what we found in the silk simulations is that as the cloud evolves, so this colors here are showing the model age, right? So the cloud first appears in the interstellar medium, it grows in mass, it has this nice atomic gas reservoir, it goes through this growth phase, and then it rapidly forms stars. So the star formation efficiency is kind of highest at the early stages in the cloud. And we can also see that in other simulations, like the Starforge simulations, simulations show that this rapid star formation period happens kind of early in the cloud lifetime. And then the best time to see this kind of equilibrium chemistry is sort of at medium ages of the cloud, where there's this steady cycling between formation and dissociation as the cloud builds. And then eventually the feedback and supernova will dissociate the cloud. So this is the story I think we can tell with individual star-forming regions. This is just one molecular cloud from a simulation. It would be, I think, fantastic to have a plot like this for each local star-forming region, to look at this as a function of GMC mass, star formation rate, et cetera. Yeah. So the second thing I wanted to bring up is, what can we do with these observations in terms of other kinds of science? And the Hyperion mission and the next proposal we'll have, which is called the EOS mission, I started getting a little sad, I guess, because once we got with the mid-X, we got a category 1 rating, which is the highest rating you can get. It means there's no major weaknesses, and usually in previous mid-X and SMEC cycles, it means you at least go on to phase A. right? Not true of 2022. There was just a lot of really high quality proposals, and they couldn't take all of them, and so they didn't take us. And of course, these things, they take time, it's fine, but it was a little bit like, oh man, like maybe no one likes the ISM. Like everyone likes transients, everyone likes exoplanets. Those things are cool. But what about H2, like molecular hydrogen? Isn't it cool? And so I started like going back to like the data that's already there, right? And really looking at it. And before I was looking at it in terms of, oh, how can we improve the spectral resolution and really get the lines for the dissociation rate? And then I started looking more in depth at the data that's here. There's a survey that was done, a Korean mission called FemSphere, and it has a R of about 500, which isn't enough to really get the dissociation rate. It's not enough to get those 10 brightest lines, but it's enough to see some of the bumps in the H2 spectrum. And then they published in a paper by Zhou et al. 2017 an H2 FUV fluorescent map. This map is very low spatial and spectral resolution. They did some adaptive smoothing, so the spatial resolution here is like a couple of degrees to increase the signal to noise. And then you can see what kind of a typical spectra looks like. It's of R of a couple hundred. But nevertheless, you can see kind of your beloved molecular clouds, a fucus, and you can see some other structures, a lot of H2 in the plane of the galaxy, which is what you expect. That's where a lot of star-forming complexes are. And then I started looking at this, and I found this structure here kind of puzzling. It looks like the North Polar Spur. It doesn't show up at all in the FUV continuum map, right? The FUV continuum is going to be scattered light from dust. It's going to be massive stars. It's going to be star-forming regions. But this structure doesn't show up there at all. And so that kind of got me wondering, what is it? And if you look at a ratio map of the FUV fluorescent H2 intensity to the total FUV intensity, so basically the ratio of these two maps, it really pops out. Right, and here's a zoom in of it. So we started calling this the EOS cloud, just to give our SMEX mission a little PR or something. I don't know. EOS cloud here. So it's a high latitude cloud that really only shows up here in the H2 fluorescence, and it's really prominent if you look at the ratio to the FUV continuum. And it really lies very much along kind of this North Polar Spur region, with which Catherine Zucker and collaborators have done a lot of work to measure the distances to. So we already had some idea that at least at these high latitudes, maybe this is a local structure. So of course, we can go look at other all-sky maps to see what we see there. So the 21 centimeter from Dickey and Lockman in 1990, basically you see that there is enough H1 that there could be H2. Right, this is very low resolution, so you're not going to really see any structure there. But what you want to see there is that there is enough, atomic gas that you could build up molecular gas there. So there should be some H2 there. So that's a good sanity check. We can also look at the H alpha. Again, that's a tracer of star formation. Nothing is there. So whatever this thing is, there's probably not any stars. You can also look at YSOs. There are maybe some young stellar objects up there with some probability of actually being detected YSOs, but nothing that would maybe suggest that this thing is really star forming. We can also, of course, look for CO, and luckily, there was a very recent release of high latitude CO map from Dame et al. 2022. So that's timely, so we could then see, there's a little tiny nugget of CO at a very local standard of rest velocity. There it is. So potentially this cloud is either on its way to forming stars or on its way out, right? But we don't see any stars there. So it's possible that this thing is maybe just starting to become dense enough and shielding enough to start forming some of the molecular gas that's dense and star forming. What about a distance here? Right, so there's a couple different ways we can start to look for the distance. The first thing we can do, maybe again like another all-sky map, is to look for the quarter keV X-rays, which are originating from the local bubble primarily, so around 100 parsecs or so region around the sun. this quarter keV X-rays are primarily coming from. There's also a contribution from the solar wind as well. And we see, like, kind of just incredibly, this cloud outline in the quarter keV X-rays. So this must be some kind of local structure that's absorbing these soft X-rays. And sure enough, if we go, so here's what it looks like with and without the contours. You can just kind of see the outline of it there in the ROSAT quarter keV X-rays. And of course, we can finally go to 3D dust maps. Thanks, this is like my last slide. And try to put a distance on this. And so with Tavisha Dharma Wardena, we've been looking at some of the 3D dust maps. And in all cases, we see essentially the crescent shape of this EOS cloud kind of forming in the 3D dust maps around between like 89 to like 95 parsecs or so. So here you can see it in one of the 3D dust maps really showing up brightly around 90-ish parsecs. So it's close by. This would also agree with other very recent studies of the local bubble showing in this region where the EOS cloud is, these are very local distances. So I think this all checks out. And we have some open questions here. In particular, the excitation mechanism, right? Because there's X-rays there, maybe some of the X-rays are also exciting the H2 lines and not just the UV. So this is something we might need the higher spectral resolution of the EOS telescope to actually address. I'm just going to leave up my conclusions. I really want to drive home that, why is it important to look at fluorescing molecular hydrogen? Maybe you're not convinced, but I really think we'll gain a lot in terms of star formation studies. Chemical equilibrium assumptions that people often make will really be challenged. We may find new molecular complexes, like super local ones, like the EOS cloud. And then we'll really be able to understand the true boundary layers of the boundary regions of molecular clouds, the initial conditions for star formation, the mass flow, et cetera, which is really the critical bottleneck for this star gas life cycle. Thanks.
Yeah, great talk. I'm going to take the privilege of asking a couple of quick questions about the Hyperion and EOS missions. What is driving the aperture? Why do you come up with 48 centimeter aperture? And related to that, what would make it so much more efficient than Hubble?
So the more efficient than Hubble is just the wider field of view. So Hubble can, right? Basically Hubble would never be able to map a molecular cloud, right? Hubble can get a very small region. That's fine. It's been, good for some protoplanetary disk studies. But to really get the PDR boundary, you need the wide field of view, the long slit. The aperture, I think, might be changing depending on some of the science goals that EOS versus Hyperion will have. I think now we have a smaller aperture, also because the cost cap is going down. Yeah.
Okay, thanks. Yeah.
Thanks for a beautiful talk. Thank you for a great talk. Just one point. You were mentioning that the molecular clouds are not in equilibrium. How does that affect the star forming rate?
So the star formation rate is very bursty. How the out of equilibrium chemistry relates to the burstiness of the star formation, I think, is an open question. Is it the chicken or the egg, right? So in the plots I showed, the dissociation rate was very bursty, right? It was kind of bursty in the same way that the star formation rate was. I think it's, these things are correlated, but which one is leading the other, I think, is not understood.
Beautiful talk. It's not that I don't like the ISM.
You have to like the ISM. Come on.
But what other science cases, specifically, for example, protoplanetary disks, Hyperion or EOS, can actually do? And have you thought, when you're suggesting the instrument, have you thought of highlighting those as well?
Yes. Good. So I've only talked about the science goals that I was primarily involved in. But EOS can also do protoplanetary disk science with R of 10,000, which is what we're proposing here. One can start to look at the H2 evaporation around protoplanetary disks. And one can also, by doing this orthopara ratio measurements, it kind of sets the stage for a lot of the chemistry as you go down and down in terms of density. And so those two cases, science cases, the chemistry modeling, the initial conditions of the orthopara H2 and the disk evaporation, I think are two really exciting, exoplanet related science cases that you might find interesting and that other people in the community would find interesting.
Any other questions? Yep.
I guess this goes back to your point of like plotting or writing down H2 and actually measuring CO. So the comparison you showed was very striking to me of the H2 contour that you're finding and then a small blip of CO. So if you just use like the standard like X factor, kind of how close do you get?
You would not see the EOS cloud if you use the standard X factor. Like you'd only see this little clump of gas, and you would miss completely the extent of the cloud.
Yeah, I think that,
so
that would make
XCO works pretty well for getting like the mass of molecular clouds, but not the volume and the extent of molecular clouds. You're completely missing the diffuse gas.
That's a pretty strong argument for emission, I think.
Thank you. Yes, hope you're on the tag.
Let's thank our speaker again.